Hello, in this video let us talk about parallel systems. What are parallel systems? Parallel systems are systems which have many processors and disks so that the performance of the system is greatly improved with respect to the execution times of the jobs that are submitted to it. Thus parallel systems are very fast. Parallel systems may be coarse-grained with just 2 to 4 processors in it, or parallel systems may be fine-grained or sometimes called as massively parallel systems, which may have processors ranging from hundreds to thousands of them, which you may find in a commercial setup. Performance measures. The first one is response time. Response time is nothing but the time to execute a particular task from the time it is submitted to the system. Related to response time, we have something called a speed up, which is nothing but decreasing the response time by increasing the degree of parallelism. Mathematically, we can define speed up as Ts by TL, with Ts being the execution time of a particular task on a small machine and TL being the execution time of that same task on a larger machine. And if the speed up is n, meaning the larger machine having n times resources of the smaller machine, we say the speed up is linear in nature. And if the speed up is less than n, we say the speed up is sublinear, as we can see in this diagram. The next metric is throughput. Throughput is nothing but the number of tasks that can be executed by the system in a particular amount of time. And with regards to throughput, we have something called a scale up, which is nothing but increasing the throughput by increasing the degree of parallelism. Mathematically, we can define scale up as Ts by TL again, but this time Ts is the execution time of a task, say task 1 on a small machine, whereas TL is the execution time of another task, say task 2, that is n times bigger than task 1 executed on a larger machine. And if TL is equal to Ts, we say the scale up is linear, and if TL is greater than Ts, we say the scale up is sublinear, as we can see in this particular diagram. And depending upon the problem size, we can categorize scale up as either batch scale up or transactional scale up. In a batch scale up, tasks are very large jobs whose execution time depends on the size of the database. So accordingly, you may want to do a scale up called as batch scale up. For example, scan of a relation whose size is the size of the database. The second one is transactional scale-up, wherein the increased database size is proportional to the increased transaction rate. For example, transaction processing systems, wherein you may have functions like withdrawal from an account, deposit from an account, etc. And as accounts are added to the system, you may want to consider transactional scale-up. Factors affecting speed up and scale up. The first one is startup cost. In a parallel system, there may be many processes, and every process has got what is called as a startup time or startup cost involved in it. So the startup times of parallel processes may kind of overshadow the actual execution times, affecting the speed up drastically. The second one is interference. Interference has to do with accessing the shared resources by the parallel processes, and depending upon the architecture, a particular process may need to wait till the shared resource is free. So this may, according to the architecture, this may slow down the system, affecting the performance of the parallel system. The next one is skew. Well, when we have a particular task, it is very ideal to divide that particular task into equally sized parts, but that may not be possible always in a parallel system. So part sizes of a particular task, when divided, may be skewed or they may be uneven. And the execution time of the single slowest part actually determines the execution time of the entire task. Say for example, we have a task whose size is 100. Ideally, it would be preferable if we have the part size as 10, so that say the speed up is 10. Say if the part size is skewed, So if the part size is skewed, or if it is uneven, we may have part sizes which are less than 10, part sizes greater than 10. Probably we may have a particular part size whose size is 20 as well. And say for example 20, this particular part size is the slowest part and this particular part's execution time actually kinds of determines the entire task's execution time. So in this particular case, what is the speed up? Yeah, you guessed it right. It is not 10, it is going to be 5. Interconnection networks. Components like processors, memories and disks of a parallel system can communicate through three kind of categories. The first one is called as the bus, wherein you have a single channel. There is a single communication bus and you have got processors, memories and disks communicating via this particular single bus, and thus it does not scale well. The next one is mesh. In a mesh system, as we can see here, which is typically a two-dimensional mesh, each component connects to its adjacent components in the grid, and the link grows as the component grows. And the intermediate nodes are used for nodes that are not connected directly. So for example, for this particular node to communicate to this particular node, it may communicate to this particular node through these two or three intermediary nodes, and it scales well. And if you actually see, a component can reach any other component by traversing at most 2 into root of n minus 1 or root of n links. For example, this is a two-dimensional mesh with 1, 2, 3, 4, 5, 6, 7, 8, 9 nodes. So in this particular example, n is the number of nodes. So any particular node can reach any other particular node by traversing at most 2 into root n minus 1 or root n links. For example, this node, to reach this node, it takes maximum 1, 2, 3, 4 links. So which is 2 into root of n minus 1 here. Or if this particular node wants to reach this particular node, it may at most make use of 1, 2, 3 links, which is root n links here. Hypercube. In a hypercube, components are numbered in binary and components are connected if the binary representations differ in exactly 1 bit, as we can see in this particular diagram. And each component is connected to log n components. A component can reach any other component by traversing at most log n links. So here in this particular case, we have 8 nodes available, and any particular component can reach any other particular component by traversing at most log n links, which is 3 links here. So a hypercube which has got say 16 links or say 16 components, and each component can traverse or reach any other particular component by traversing at most 4 links, which is much more efficient than mesh. So you have a lower communication delay than in mesh. So alright, so these are the interconnection networks. So we will stop our discussion here and continue our discussion in the next class. Thank you.